Okay, so we look at L2 of gamma, and this has almost invariant vectors. Okay, and then I look at the H action on gamma. Okay, so gamma has H cosets, and if I was talking to some of you about this, I incorrectly decomposed gamma as left cosets, and since I'm looking at the left regular representation, that's what kind of went the wrong way. So that's not what you want to do. You want to look at right cosets. Okay, now H acts very nicely on this, and we have that L2. This is from the first or not the first exercise, but one of the exercises before this one. Decomposes. Here, what is S is my coset representatives. Okay, I'm writing S so that it matches what you did in the other exercise. And this is L2 of HS, S and S, right? And this isomorphism is H equivariant. That was part of the exercise as well. And now you just want to say that if you have gamma almost invariant vectors, okay, this has almost invariant vectors for gamma. Well, H is a subgroup, so it also has almost invariant vectors for H. So those almost invariant vectors become almost invariant vectors here. Okay? Everybody okay with that? So now where do those almost invariant vectors, is that okay? Yeah? So if I have almost invariant vectors here, this is a gamma or H equivariant isomorphism, so they just are over here now. But each of these is H equivariant, H invariant, okay? So each of these factors. So my almost invariant vectors, they have a large projection, this is important, a large projection in some factor, okay? So you got to find the factor and then show that that's actually isomorphic. You want to show that these are isomorphic to the left regular representation, but hopefully that's pretty obvious. Okay? So everybody good with this isomorphism? The almost invariant vectors survive, but they could be like a little bit from the first component, a little bit from the second component, and so on. So you have to show there's a large projection in one of the components. Okay? Questions?
What do you mean by large projection?
I mean that they don't go to 0. Okay? So let's start back.
Why is that the problem if they go to 0?
Because, so remember, when we're looking at so when I said you have almost invariant vectors, yeah, right?
So VNs individually could go to 0.
If I don't have this here, the Vn could go to 0, and then, yeah, okay? So making sure they don't go to 0, if you want, making sure you can normalize them to be unit vectors, yeah, okay? And keeping this condition, yeah. Okay, so, yeah. Should I start, or I didn't mean to stop everyone from talking. Since you were all here, I just thought I would address that. Should I start in like 1 minute? Can I erase this? So oftentimes we write gamma mod H. And this is where I've taken a quotient by the right H action. So that means that everybody looks like a right H orbit. On the other hand, I have a left action for H, which corresponds to right cosets. And sometimes we just write this as like X And sometimes we write it like that, depending on what's convenient. Yeah? Should I start? Yeah. Actually, let me get my water. Thanks. Okay, so last time we were discussing this short exact sequence lemma, where if I had relative property T with respect to the end groups, then I had it for the middle, and conversely. That was an exercise that I kind of started for you. We proved that compact groups have property T, and I don't think I had written this down. Maybe I had, but I'll just start there. So it's an exercise. So show that if H is in G, is closed, and H has property T, then GH has property T. Okay? And we're going to use that soon. Yeah, so maybe I'm going to go ahead. No, I'll just write the corollary. So a corollary to the lemma that we had yesterday is assume that A1 goes to A, goes to V, goes to T, is a short exact sequence. And gamma maps to the automorphism group of V that preserves A. Okay, everybody remember this? I'm acting by automorphisms of V, but I'm also preserving A as a normal subgroup. Then, okay, period. Gamma semidirect product A has relative property T. If and only if, oh, I forgot the other assumption, sorry. T has property T. Then having relative property T for A is equivalent to having relative property T for B. Okay, so I got rid of the assumption on the quotient by just making it have property T. And in practice, what we're going to do now is assume that it has, that it's actually compact. So there's spaces up here. Don't be shy. Come. Yes. This is the good seats. Okay. And if it starts raining, which it probably won't, you'll be able to hear me. Okay, so this is a new version of the lemma I put up yesterday for those who are just coming in. Yesterday we had an added assumption. We've swapped out T has property T here for the assumption that I had relative property T with respect to T as well. So this is what we're going to use. And I want to just give you an example of gamma. Yeah. Mm-hmm.
This is no longer if and only if.
It is.
It is? Okay.
Yep. So these are my hypotheses. And then this is if and only if this.
Oh, okay.
Okay? Okay, so as an example, I've made A for like abelian, V for vector, and T, not just because it has property T, but kind of like a torus. So the first example we're going to have of something that we can feed into this sort of machine is going to be gamma mapping into SLN-Z, for example. A will be Z to the N. V will be R to the N. and then T would be the torus, V mod A. Okay? Another example, which is related also to one of the homework problems, is gamma mapping into SLN Z adjoin 1 over P. Okay? So this is the ring where I have the integers, and I've allowed myself to invert just 1 prime, P. And now A here is going to be Z adjoin 1 over P to the N. V is going to be actually no longer a vector space. It will be Rn cross Qp to the N. And then a fun exercise to do is to calculate what this quotient is. And this is, again, I'll write V mod A. This is a, let's say, P solenoid. So the exercise that that I asked you to do, if you know the p-adics, is to show that Z adjoin 1 over P embeds discretely and co-compactly in R cross QP. Okay. Actually, this is an n-dimensional p-solenoid. But here, this is a p-solenoid, the quotient. And of course, everybody knows that the rationals embed into the reals, but they also embed into the p-adics. In fact, the p-adics are the completion of the rationals with respect to the p-adic norm. So I have a diagonal embedding here. And you can just play around very directly and show that this is proper, that it's discrete and co-compact. Okay, so you can find a pre-compact fundamental domain. Okay. So these are some situations. Okay, one more example. Another example would be that A is O, the ring of integers of a finite extension of Q. And then it's known that depending on which, yes? Close the window. Can I close one window, or is that okay for everybody? No. Oop. Okay.
Yeah, probably that was worse.
Okay, should I try this one again?
Yeah.
Okay, I like windows. I don't actually have a window in my. Open it again?
No, it opened itself again.
Like this is okay.
This is open.
This is bothering you?
No.
Yeah, it's okay. Just your OCD a little bit. Okay. So we know that that the ring of integers in a finite extension of Q, well, the finite extension of Q itself will admit multiple Galois embeddings into the reals and into the complex. And you have to count those, the complex ones up to complex conjugation, blah, blah, blah. So here, I'm going to just put R question mark cross C question mark. So I need to look up in a number theory book how many copies of R and how many copies of C I get. But now I need, rather. And the quotient here, T equal to the quotient, will be, in fact, a torus. A standard torus of the dimension corresponding to 2 times what I have here plus 1 of those. Okay? So, and then of course, gamma would be mapping into SLNO. Right. Sorry, this would be, that's all true, but then I'm going to raise this to this power because of this n. Okay. And then now that I have this, I can also invert some primes that might have split when I looked at this algebraic extension of Q, and blah, blah, blah. Okay, so you can mix this with that, and so there's lots of things you can play with here. So we're going to be discussing now is a special case, although everything that I have said this week can very easily be modified to prove all of these over here with appropriate hypotheses, of course. So so theorem. I'm stating this as a theorem, but it's really a corollary of that corollary. So if I have a representation of gamma into SLNZ, which I will remind you has finite index in the automorphism group of Zn, which is a subgroup of the automorphism group of Rn, which is GLNR. Then we have that gamma semidirect product Zn has property T, relative property T, if and only if gamma semidirect product Rn has property T, relative property T. So my objective is to give you an honest proof, an example of a pair with relative property T. And our main objective, since we're studying discrete groups, is going to be to think about this one. But the proof is going to be much simpler. So these are going to be equivalent. Okay? Right. I realized, any questions? So I realized as I was looking over my notes that I was doing something that used to drive me crazy when I was a graduate student, where I would read a book and they would be like, this is true, this is true, this is true, and now I've proven this, okay? And I wasn't like warned that you were about to prove something. So let me give you a little warning about why I'm gonna start talking about what I'm gonna start talking about. Okay, so let's see. Oh, yeah. So I want to have a condition that's going to tell me about the relative property T for this pair. And that's going to come by Berger's criterion. Okay, so assume that phi takes gamma to PGL, nope, just kidding, GL and R is a homomorphism, and there are no gamma invariant probability measures on P of Rn. This is a lie, so keep track of my lie here. I'm about to fill it in, but I'm going to finish the lemma, whatever, the proof, the statement. Then, so this is the projective space, then gamma semidirect product with phi Rn has relative property T. Okay? So what was the thing that I omitted there? Well, what is relative property T about? It's about unitary representations, right? So this here doesn't appear to have anything to do with unitary representations, and that's exactly the lie that I have omitted. What I need to put here is the unitary dual of Rn. Okay? So we're going to talk about the unitary dual of Rn basically now, but just a quick fact is that as vector spaces, these are isomorphic. Okay? So why is it important then that I put this hat here? Because the hat is related to this representation. Okay? So Berger says, if you do not have an invariant probability measure, now we know what you look like if you have an invariant probability measure. If you don't have an invariant probability measure, then you have relative property T. Okay, so we're going to talk about that proof, and then we're going to use that to prove that certain representations will give us relative property T. Okay, so that was my little intro to why I would start talking about unitary duals, okay? Okay, so R is a local field. So it's locally compact with respect to this norm that we have, and it's a union of compact sets. Okay, so that means that Rn hat, okay, which is by definition the set of pi from Rn to the unitaries of a Hilbert space such that pi is irreducible, okay, which is, I'm going to explain this, is isomorphic to Hom of R and S1, which is itself isomorphic to Rn. Okay, so what is an irreducible representation? What do you think? There's no non-trivial sub-representations. So irreducible, pi from from gamma to u of h is irreducible if there does not exist an h prime in h that is non-trivial, in just a second, not all of h and non-zero, that's gamma invariant. Yeah.
So, the definition of local field, you require the union of compact sets. But could you just take all the points and those are compact sets and?
Oh, thank you. A countable union. Yeah. Thanks. Good catch. Okay, so what is an irreducible representation? And H prime is closed. H prime is closed. Thank you. Variant. A Hilbert subspace. Hilbert subspace, i.e. in particular, it's closed. Okay. Other remarks or questions? Okay, so that's what it means to be irreducible. And I'm not going to prove this isomorphism, but this uses Shor's lemma. I am going to talk about why these are isomorphic. So I'm going to assume this, and I'm going to explain this isomorphism. So, right. So look at so I'm going to wait, was I supposed to put an isomorphism there too? I guess so, but let me stick to that and see if it works. Okay, so I'm going to, so there are two duals of Rn, okay? There's a linear dual, and then there's this unitary dual, and they're the same. But the way that you realize them is slightly different. So let's actually take, okay, so this is, I'm not taking this as a definition. I'm going to take this as another isomorphism, And then Rn dual is going to be the linear functionals from Rn to R. So linear. Okay, so you can work out pretty quickly that this is isomorphic to phi of, this is generated by, let's say, phi1, or this is equal to, let's put it this way, phi1 to phi n, where phi I applied to a vector v is your favorite inner product of vi against vj, vi against v. And actually, I want to use a j here because I'm going to use I, the square root of -1 in a second. So this is has a vector space structure. It's generated as vectors by these maps. And I'm going to define a map to the homomorphisms. Okay, so, right. So what am I going to do? Oh yeah, I want to tell you what this is. So my favorite inner product is this one. Okay, that's going to be relevant for understanding which representation I'm going to get when I'm looking at this. So, right. So what am I going to do? I'm going to now define pi sub j, which is going to be a map from Rn to S1. So it's going to be a character. And what's it going to be? Well, I need to tell you what it does to a particular vector. I'm going to use phi. It's going to be e to the I phi j of v, which I will remind you is e to the I inner product vj with v. Okay, and then this I here is not an index set, but the square root of -1. Okay, so this is a character. I'll let you check it. It's a homomorphism into the unit circle in the complex plane. And you can also check that all characters are of this form. Okay, so this inner product gives me a duality between Rn, between Rn and its linear dual, and by exponentiating it, it gives me a duality between Rn and its unitary dual. And then, of course, you get that the linear dual of the linear dual is back to where you started because of the nice structure of the inner product. Okay, so all of that, I guess I didn't really need to talk about these irreducible unitary representations. I could have just talked about the linear dual, but I wanted you to see what the connection is. Also, if you want to do this directly, I guess I erased it. If you want to prove directly the relative property T of gamma with Zn, then you will need to look at the unitary dual. And that's actually what Shalom does in his bounded generation paper. Yeah?
Unitary of the Hilbert is any Hilbert space or any Hilbert space?
Yeah. So basically, because Rn is abelian, irreducibility is going to tell you you're one-dimensional. Yeah. Okay. So I want to come back to what's happening over here, because I want to understand what is happening between my sort of standard representation for gamma and how it's acting on this dual projective space. Okay, so observe that, okay, so what do we have? Rn is vector isomorphic, as a vector space is isomorphic to its dual. And so you could ask, do I have isomorphism on the level of the general linear groups, okay? And the answer is yes. If I take a matrix here, I'm going to make, Yes, who said? Transpose. Thank you. Yes. I mean, thank you for saying transpose. It's no, but you're very close. Okay, so if I take a matrix here, you would think that it's the transpose, right? That's the whole reason I was talking about this mess, was because I have a transpose here, right? But I don't want it just to be a map. I want it to be an homomorphism. And what do I know about the transpose? N is bad. Let's do A and B. What do I know about the transpose of two matrices? It's the opposite order, right? So it's not a homomorphism, okay? Now, what else do I know that has this property? Inverse. So you could just be like, well, maybe now I've fixed my problem. Oops. I fixed my problem, but that doesn't mean that this is what I want, okay? So this certainly does give me isomorphism between GLN-R and GLN-R, but is it the map that I want here, okay? Where did this inverse come from? That's number one. And also, I just want to mention that this is the only automorphism up to conjugation that is not conjugation of GLN-R. Okay, so inverse transpose is an important map, but is it the map that we want here? Okay, so to do that, we need to study this a little more carefully. Remember when we were looking at, can I write like just a little bit lower here? Is that okay? I'm always trying to get away with just a little bit. Okay, so when I was looking at L2, remember when we were looking at acting on functions? What did I have to do to X in order to make this an action? I hope everybody checked that it was an action. What happened? It became inverse, right? And I hope you checked why you needed that inverse. So basically, whenever a group element moves past a function, it has to change signs, okay? It has to change. You have to make it an inverse. So if it moves past two functions, then there's no inverse. So that's exactly where our inverse is going to come from. So my matrix M applied to phi j. I'm going to apply this to V, okay? The phi j's are maps, which means now you know because you checked it in your homework that I need to put an inverse. Otherwise, I don't get an honest action. And then this is going to be Vj applied to Vj against M inverse of V, and because we know how the definition of the inner product, that this is going to be M inverse transpose Vj V. And I guess technically over here I wrote A transpose inverse. Everybody knows that transpose inverse is inverse transpose. And so we get exactly what we want. Okay? Make sense? Okay, so does it make sense? So yesterday, okay, so that's the end of this little explanation. I'm not sure if that really deserves a little box, but I just want to recall that yesterday, in answering the question, what was the closure, or given gamma inside PGL and R, what did it mean to be amenable? We got that gamma was contained in this upper block let me put compact. So K here is just like a random letter for a compact set, compact group, right? So I got compact things on the diagonal, stars above, and 0. So what's going to happen under this new representation, which I have erased, or this one? Well, it's the inverse transpose, but the inverse of a group is. So this thing will become the transpose is going to become the same form, but on the lower block. Okay? And that's not really going to be that important, but I just want to make sure that everybody understands, like, where, you know where you are, wherever you are. Okay? Okay. Right. So that was a little word about the dual of Rn. And now we're going to continue to use the fact that Rn is abelian. We used it here to understand more general unitary representations for the semidirect product. I think I'm going to, since I'm kind of starting a new thing, I'm going to start it here. Okay, so Rn is abelian, if you didn't know. Okay, and this is really, really going to be fundamental to everything that we're going to be saying now. If it wasn't abelian, you could, if it was, say, like nilpotent, one step nilpotent or solvable, you could maybe put these tools together, but everything here is really for abelian groups. So fix pi semidirect product Rn to unitary representations on H. Notice I have dropped my acting map phi, okay, but it's implicit. And I'm no longer assuming this is irreducible. Given such a unitary representation, there exists P from the Borel sigma algebra of Rn dual to projections on the Hilbert space. Okay, I'm going to explain that in a second. Let me just say here, this is Borel sigma algebra on Rn dual, and these are the set of projections in H. Okay, doesn't really matter, but that they satisfy this property. And they satisfy, so given such a pi, there is a p sub pi, which I'm just going to call p because pi is going to be fixed, satisfying the following properties. So let me say again, p is p sub pi. So I'm supposed to be assigning for every Borel set a projection, okay? So what's an example of a Borel set? Everything is a Borel set, Rn dual. So this is going to be the identity. The identity is a projection. What else? For every V in V, the assignment, yes, thank you. Orthogonal projections. Thanks. For every V and V, the assignment B goes to, what do I want to say? P of B, V against V, okay? this is going to have some property, but let's think about what property it might have before I tell you what the property is. So V is a vector. That means I can project it. Okay, I get a new vector. Now this is an assignment taking Borel sigma, the Borel measurable sets, to what kind of object is this? It's a complex number, right? So this is a complex number. Actually, it's going to be a real number. That's part of the condition. And I'm assigning to each Borel set a number. So I want this to be a positive Borel measure. Is a positive Borel measure. Okay? So every vector is a measure. Or rather, every vector paired with this projection valued measure is a measure. Okay? So let me put up another property up here. So P of 0 is the projection onto the Rn invariant vectors. Okay, so if my pi has Rn invariant vectors, then this would be a non-trivial projection. But if there are no invariant vectors besides 0, this would be the 0 projection. Okay, so this particular projection is really controlling what I want. Okay, right. So there's another property here, which is going to be the relationship between gamma and p. But before that, I just want to kind of summarize why this is called, I didn't write it down. Sorry about that. So P is a projection valued measure. Okay. So what is a measure? It takes Borel sets to numbers, right? Well, this one doesn't take Borel sets to numbers. It takes Borel sets to projections. And those projections behave like a measure. Okay? So it's a little weird, but it's okay, right? Okay. So the last property is that for every gamma and gamma, pi gamma inverse P of B pi of gamma. So if I conjugate by gamma, this is P of gamma star B. Okay? Okay. So, okay, what is the star doing here? Well, B belongs to the Borel sigma algebra on Rn dual. So that's my sort of local notation for the inverse transpose, okay? So this is not an inverse transpose because this is just like my normal group. And now it has become inverse transpose when I apply it to B. Okay? Okay. Don't be scared. Okay? Yeah, so let's pause a moment and try to maybe unpack a little bit of what this projection valued measure is doing. Okay, so it's a map from Borel sigma. I've said it 10 times. I'm going to say it one more time. I take a Borel set here, and I assign a projection. Okay, so let's say I have 1 point. That's a Borel set. And I could assign a projection. Okay, that 1 point is in the unitary dual. So how much, so this projection is kind of picking up how much that irreducible component is part of this unitary representation. So let's look at an example.
Maybe you can say what this projection value measure is in case H is finite.
I'm giving an example, yeah. So let's look at an example. So pi is taking R to C cross C. So n here has become 1. Okay, this is an abelian group, which is also a vector space, which is, okay, this is just R. And I'm taking it to C cross C. And it's going to be a little more, C and C are the same, so it'll be a little less confusing, I think, if I call this V1 and V2. It also gives me a more sort of general example if you replace C with another vector space. And pi is going to take x and evaluated at V1 and V2 is going to give me e to the ix V1 and e to the 2ix V2. Okay, so it just so happens that my indices match these powers. So 1 with 1 and 2 with 2. Okay, so now P is supposed to assign to every Borel set, blah, blah, blah. But in this case, it's just going to be a function. And I'm going to tell you what that function is as a function of functions. Okay, so phi here is supposed to belong to the unitary dual, or the dual, unitary dual, right? So p of phi is going to be a function, and this is going to be the projection onto Vj if phi is equal to phi, if phi is equal to j, phi is equal to j. That does not make sense. 0 otherwise is going to be the v. Sorry. So I'm projecting the dual. Oh yes, that's right. Okay. Phi here is a real number, and that's what I wrote, but I got myself confused. So phi. Yeah. So I'm looking at the dual of R with itself. The dual is, again, R. J is a real number and an index. So if J is equal to 1, this is the projection onto the first coordinate, which corresponds to the pairing EI times to the power x. And then this one corresponds to the pairing with 2. OK? Was it a little too simple for you to follow? Sometimes when examples are simple, it's hard to follow. So I find. So remember I had this unitary dual here, right? So this was supposed to be an inner product, right? But it's not an inner product. I just have numbers. So I'm just multiplying the numbers together. So the number here, this is e to the I inner product, right? Well, it's just a 1, and it's a 2. And that's why I have here j 1 and 2, OK? So if my character corresponds to the number 1, I'm projecting to the first factor. And if my character corresponds to the number 2, I'm projecting to the second factor. OK? And it's 0 otherwise. How many quote unquote copies of e to the 3ix? So this is an irreducible unitary representation from R to C. How many copies of this do I see in this particular representation? None, right? So I have the 0 projection. OK? Make sense? This is a 0 projection, not the 0 number. OK? Good? Yes?
So should it be for Borel subsets of R then?
Yeah, so now, so this is like a Dirac mass. OK? So this is just telling, it's going to pick this up if this number is in the Borel set, and yeah. So it's a very simplistic case. But that means I could have much more complicated, say, functions, or much more complicated behavior. Okay? Good point. Okay.
I have a quick question.
Yeah.
So pi was supposed to be taking in as input something in gamma direct, semi-direct product RF, right?
Yeah. So yeah. So good point.
As in here you
Here I forgot my gamma. Say, I was just giving an example. If you want, I can call this like rho, or let's call it rho. Okay? So that we don't get confused.
and over here.
No, over here it's okay. What?
So what is pi of gamma?
Pi of gamma is the image of gamma.
Um,
So
as
pi,
in not as-
pi is, so are you wondering about the R component?
Yes.
Yeah, so it's trivial in that component. So remember yesterday when I was discussing the semi-direct product, I said it was a product as a set, but I wasn't going to write the parentheses and the comma. So there's a secret no.
So for any Rn vector, it's the same.
Say it again?
So is this also true for, I mean, is it more proper to say pi of gamma times A, where A is some Rn vector?
No, I'm specifically talking about, right? So this means that gamma is a subgroup, right?
Yes.
So I'm only talking about gamma,
Okay.
okay? And it's true, it's probably about what you were about to say. So far, my main group was always called gamma, and now my main group is gamma semi-direct product Rn. And that's probably why you're having this, is that what you were about to say? If not, then just hold that thought. So this is a locally compact group. So it's, if you want, a G. It has two pieces. It has a discrete piece. I'm really going to be thinking about gamma later as being in SLN-Z, so it's discrete. And then it has this like locally compact piece. And here I'm really talking about gamma.
Okay.
And why? What's the point here? Remember, Rn is normalized by gamma. This projection valued measure always exists independent of whether I have the gamma or not. It's a property of Rn being abelian. Okay? So all of this is about Rn until I get to here. And this is telling me the relationship between the action of conjugation of gamma on Rn, namely the normalizing action, and how it's acting on this projection valued measure. Okay? Yes?
I was to say two things. So, you didn't write, you didn't write all the properties of the projection that you measured.
I wrote all the properties that I'm going to use. There's lots of properties.
And just, okay, so just a philosophical comment. So in the example that Talia explains, if you have an action, a unitary representation, which is finite dimensional of an abelian group, so you can diagonalize simultaneously over the matrices. So basically it says that you are a direct sum of one-dimensional representation when you act by multiplication by some kind.
A direct integral.
No, I said finite dimensional.
Oh, sorry. Yeah.
So you're a direct sum of a one-dimensional thing, and what this projection valued measure are useful for, what they do is to make a sense of this for infinite dimensional representation, to give a meaning to the fact that a unitary representation of an abelian group is a kind of integral of one-dimensional thing.
Yes. In fact, somebody was asking me yesterday, isn't it true that all the representations, unitary representations, are direct sum of irreducible ones? No, but they are direct integrals. And this projection valued measure is exactly going to tell you how to disintegrate it. Okay.
Actually, an exercise. Take the regular representation of R on N2 of R by representation. Side, the
Okay.
the answer is in one of the two couple of things.
Rudin. Okay, so that's what a projection valued measure is. Actually, when I was preparing this, yes,
In the second bar, the second star, I don't know what is the capital.
Oh, yeah. This is a Borel. Let me put it this way. B in, yeah?
The previous
H maybe.
it's H, right?
I don't know.
On the for all B in H. Should have been for all B in H.
This one or this one? Okay.
Second star, for all
For all B in H, possibly.
your vector is in H.
Oh, sorry. I'm like, I don't understand. Yes, B, sorry. So, yeah, I've been calling the subgroup H, and sometimes the H and the H kind of get in the way of each other, and so sometimes I switch to V. Sorry. Yeah, thank you. Other comments? Okay, so, right, so that's a projection valued measure. This always exists. I don't need the gamma, but if I do have the gamma, it behaves nicely in this way. Okay? Okay, so now we're ready for Berger's criterion, which I guess I will write over here. So, oh wait, I already wrote Berger's criterion, but you probably don't remember what it is because it was a while ago. Let me write it again. So phi from gamma to GLN R with no gamma invariant probability measures on P, R, and dual, the projective space, then gamma symmetric product Rn with Rn has relative property T. Okay, and I'll just say that the proof here is somewhat a combination of Berger's original proof and Shalom's from the bounded generation paper. And I'm not writing Berger's title because it's the only one in the references, but it's called something like Kazan constants for SL3, or I don't know, something like that. Okay. So what do I want to show? I want to show that my semidirect product has relative property T. So what do I want to start with? A unitary representation with what property? Almost invariant vectors. Very good. So proof. Say pi is a map from my G to, which is a semidirect product, to unitary on H with almost invariant vectors. Okay, so what are they? They're my VNs. Let's write them over here. Okay, so what can I do with a vector and my, well, then there is a projection valued measure from the Borel sigma algebra of Rn dual to projections of H. Okay? So what is the only thing I know I can do with a vector is I can take this inner product and I get a positive Borel measure with another property that I actually forgot to state. Although I guess it follows from what I have here. So if I combine both of these together, this property and this property, it means that the total mass of the measure, let's say mu sub v, right? So the assignment B goes to this projection V against V is supposed to be a Borel measure. So this measure has total mass equal to V squared, okay? So, right, so that's going to come in handy now. So I have a projection valued measure, and I have a sequence of probability not probability measures, but of vectors that are almost invariant, okay? And I'm going to assume by contradiction that I do not have Rn invariant vectors, okay? So I want to show I have relative property T. If I have almost G invariant, then I have Rn invariant. By contradiction, assume I don't. And P of 0, the identity in Rn, is the projection onto the Rn invariant vectors. I'm rewriting what I have there because I'm going to erase it. And assume by contradiction that this is the 0 projection. Okay? The projection onto 0. The 0 subspace. Let's write it like this. O in H. Okay? The 0 subspace has its own projection, and I'm projecting onto it. Okay. So I have this sequence. Okay, maybe I'm not going to erase that. All of my erasers have accumulated over here. Okay. Okay, so I have this total mass. Okay, so let's continue. So define mu sub n b to be P of b Vn Vn. Okay, this is a Borel measure, as I stated. Okay, and how much mass does it give to the 0 set, or the set of the 0 identity element in Rn? Well, I'm supposed to take this projection, right, and hit it against Vn. So how much mass do I get? 0, right? It's 0 against Vn. Everybody get clear on that? Okay? Yeah? Okay, I see like some nodding and then some people doing like this. Okay, so this, let me write it down. This is the projection onto the 0 subspace. I don't know if that's clear. Vn against Vn, this is 0, this is 0. Okay? So this measure has no mass at 0. So what can I do? I can projectivize it. Okay? So I'm going to look. Do I have a notation for that? What?
The square brackets you were using there.
I was wondering if I had some local one in my notes so that I wouldn't confuse myself. Yes, I have a bar. Okay, so now the square bracket was for points. I'm going to put a bar. So now I'm going to look at the push forward. Measure, which is going to be the push forward under Rn minus 0, which I can do because 0 has no measure, to Prn. Okay, so I have this map, and I'm going to look at the push forward measure of mu n mapping to mu n bar. So this is now a measure on the projective space. Okay, and okay. So when we were doing Furstenberg's lemma, sorry, not Furstenberg's lemma yet. So right, so now what do we have? Combining this here and the fact that I'm looking at the push forward measure, I'm going to get, and together with this one, okay, I'm going to get that gamma star mu n minus mu n is going to be equal to twice the sup over the Borel sets of gamma star mu n b minus mu n b, which I leave you as an exercise to show that this is less than or equal to twice pi of gamma Vn minus Vn divided by Vn. Sorry, you know what? I was supposed to normalize, I think I was supposed to normalize these to be probability measures. Sorry about that. Here, okay, unit vectors. Everything I've said is true, but I want these to be unit vectors, and now I want to say that this is going to 0 as n goes to infinity. This is equal to 1. Okay? Sorry about that. So what's going on? I start with a unitary representation of my semidirect product. I restrict it to Rn, which is what I'm interested in studying. And by contradiction, I assume that I have almost invariant unit vectors, but not Rn invariant vectors, which tells me that this projection is 0. And then using the properties of the projection valued measure tells me that I have 0 measure at 0, so I can projectivize them. And once I projectivize them, well, I can put a bar here or not a bar here. So first, I guess I could have not projectivized first. These have this property, and so they still have the property when I projectivize them. Okay, because the push forward is just the push forward. Okay, yes, please. Yes, thank you very much. This one has a hat, and this one has a hat, and this one has a hat. And yes, thanks. Okay, so Right. So where are we? We have a sequence. This is for every gamma. So mu n sequence of almost invariant vectors, almost invariant measures on the compact projective space, right? And with a little dual. Okay? So what do I know about probability measures on a compact metrizable space? Anybody? So, what?
Something about the dual.
Yeah, okay, so the Banach-Laoglu theorem says that the probability measures on a compact metrizable space is weak star compact. Okay? What does that mean? It means I can take my mu n bar and find a weak star limit, a weak star limit point. Okay? So up to passing to a subsequence, the mu n bar will converge to, let's say, mu infinity bar. So now, what property is this mu bar infinity going to have? Well, it's a limit of these measures. And these measures are asymptotically gamma invariant. So they will be gamma invariant. Okay? Or it will be gamma invariant. And mu infinity is gamma invariant. Okay? Okay. So I'm done. I don't have it written down anymore, so let me write it again. Which board do I'll just write it here. So we had these properties. Okay. So Berger's criterion was, so gamma is acting on GLN R if gamma does not have an invariant measure on PRN dual, then gamma semidirect product Rn has relative property T, right? That was our objective. And I guess it was really a proof by contrapositive. We assumed that there was a pi from gamma semidirect product Rn to the unitaries with almost invariant vectors. But no Rn invariant vectors. And the lack of Rn invariant vectors allowed us to projectivize the measures we were given from the projection valued measure. And then once we were projectivized, we were able to find a convergent subsequence, which was in turn gamma invariant. that's what happened over here. And therefore, I had a gamma invariant measure. So if I fail to have relative property T, then I have an invariant measure. OK? Good. I like smiling and nodding. OK. So I have 3 minutes. So let's put this together. So we have Furstenberg's lemma, which says that if gamma is in P, G, L, and R, and mu, let's call it mu infinity bar, since that's what I'm going to apply it to, is gamma invariant, probability measure on the real projective space. And actually, let's go ahead and put a hat here, since it's also what I'm applying it to. Then there exists a V0, which is non-trivial, and also non-zero V0 subspace, which is almost virtually gamma invariant, and mu of V0 is positive, right? That was what we proved. So let's put these things together. So if I fail to have an invariant measure, then I have relative property T. Well, how can I fail to have an invariant measure? Oh, oops, I forgot the not precompact. Then either gamma is precompact, or there is such a thing. Well, let's look at a really simple case. So example, gamma is SL2Z. And this is acting on R2, so I'm looking at gamma semiric product R2. OK? Is SL2Z precompact? It's not. OK? Does it have an invariant subspace? It does not. OK? Does it have a finite index subgroup that has an invariant subspace? It does not. Right? Everybody agree with those statements? So the conclusion is that gamma semiric product R2 has relative T. And as I had said before, this is if and only if gamma semiric product Z2 has relative property T. OK? But actually, the n equals 2 case is so small that I can get away with a lot less than being SL2Z. OK? So so I know I'm out of time, but let me just say one more word. So I'm going to look at a subgroup now of SL2Z, or just any group mapping to such a subgroup. So I want to avoid being precompact, and I want to avoid preserving a subspace. OK? Well, one way to do that, and I'll leave it as an exercise to verify, is I can take my gamma to be generated by any unipotent I want. So pick your favorite integer, let's say 13. 11301 is one of my generators. When I projectivize this element, I'm going to have one fixed point. It's actually the projectivization of the transpose, but whatever. It's going to have one fixed point, and I'm just going to make sure that my other generator does not have the same fixed point. So I can put, I don't know, give me a number. Too slow. 13 to the 13, 0, 1. Okay? So the fact that this is unipotent means that it's not precompact. And the fact that these have different eigenspaces and the dimension is 2 means that they don't have a fixed point in the projective space, which would be the only option. If n is 2 and I am not everything and I'm not 0, then I'm 1 point. And so this also has relative property T. So any non-amenable subgroup of SL2Z with R2 and therefore Z2 has relative property T. Okay, so thank you very much.